Today's webinar will cover the new features and development in the mantle convection and lithospheric dynamics code aspect version 2.0 and is presented by Rene, Gassmöller, Juliane, Dannberg, Menno, Fraters, and myself. And in the interest of time, I will turn it over to Rene now.
Okay, thanks, John. As John already said, today we'll be hearing about the news and developments in Aspect 2.0. And before I start, I would like to mention that although myself, Juliane, Menno, and John will present these new results, they are really a collaboration of many, many people, in particular including Wolfgang Bangerth, Timo Heister, Anne Glarum, and Jackie Austerman, but also many more contributors that I cannot list here because the slide is too small. Aspect stands for the Advanced Solver for Problems in Earth's Convection. And before we come to the new features of this release, I would quickly review what Aspect is about. So Aspect is a code that tries to use modern numerical methods such as adaptive mesh refinement, linear and nonlinear solvers, higher order discretizations, and offers multiple ways to advect information through the domain. We try to focus on usability and extensibility of the code, in particular by providing a big manual. We now have around 40 cookbooks or example models that you can use to start your own models from. We have a big test suite, and we provide a plugin architecture that allows to extend the code into all kinds of different fields. The code has been tested to be parallel scalable up to thousands of cores, and we try to build on other libraries' work to have a tested foundation for our software, to reduce the size of our software, and to get the automatic improvements from our upstream packages. But one of the really defining features of Aspect is that it is a community code, and it's a community code in the true sense. That means it's published with an open source license. The development happens in the open. You can watch the development on GitHub, and we try to encourage contributions from everyone by forming a welcoming community, by answering questions on the mailing list, and just in general by welcoming people into the community who want to participate. You can find out more about Aspect on our website, aspect.geodynamics.org, or on the GitHub webpage, github.com/geodynamics/aspect. While there are 4 principal maintainers, we have 4 more principal developers and many, many contributors, and you can see all of them on GitHub. And it was started in 2011, the software project, and up to now we have around 30 publications citing it, with an increasing number of publications per year. So let's come to Aspect 2.0. Why did we decide to make a new major release for Aspect, and what are the reasons behind that? There are essentially 2 main points about why we decided to make a new major release. Technical reasons and new major functionality. The technical reasons are that Aspect has grown enormously over the development time from 2011 to 2018. We now have over 7,000 commits on GitHub. We had 9 releases in that time. We have much more functionality than at the beginning. And whenever a project grows this fast, you have developments that don't quite hold up to the quality that you expect for the whole software package. In software development terms, this is known as bit rot, or the continuous degradation of the code base that you try to develop. So you need regular cleanup. But not all of this cleanup can be done in a backwards compatible way. Sometimes you have to change names, or you have to discard all functionality that's not longer relevant. And in order to provide this, and in order to improve the modularity of Aspect, we had to make some breaking changes. In general, these changes were done carefully, and we tried to only break things that would allow us to grow Aspect further into the future. The second major reason was that we have new functionality, and important new functionality in Aspect. For one, we have an extension of the two-phase flow solver that was in Aspect since version 1.5. We have a new Newton solver for the Stokes system that Menno will talk about later. We provide a new small standalone program called Aspect GUI that allows to graphically create to create input files for the model run. We have a model for grain size evolution, a model for dynamic core temperature evolution, and many, many more significant changes. On our website, you can find 107 significant changes in this version, not to mention all of the small bug fixes and improvements. Before I start talking about the major improvements in Aspect, I would like to start with one minor thing, and that's improving reproducibility of model results. Reproducibility and replicability of scientific models are a key feature of the scientific method, and they are becoming more and more complicated the more the science and also the more the software advances over time. So the more dependencies your software has, the more complex it is to recreate this exact model. Aspect always reported its own version in every model output, so that allowed for some replicability of the models of Aspect. But starting from Aspect 2.0, Aspect also reports all of the versions of the libraries that it used and the exact git commit hash for the Aspect version, which does not provide perfect reproducibility of this model, but at least it's a much better situation than before. Also, we now provide information about how to cite Aspect in every model output to make it easier to give the attribution to the software package, which is an important part because software citation becomes more and more important for journals and publishers. Now, when I talked about the improved modularity in the beginning, what do I mean by that? From the beginning, Aspect was designed with a plugin system, which means the core part of the program, the Stokes solver and the solver for the ejection equations, which is shown here in the middle box, was separated from parts that often have to be changed by users by interfaces. And each of the parts that often has to be changed was provided as a plugin system. So there were plugins for initial conditions, for boundary conditions, for the geometry, or for the gravity model. And the same is true for material models, post-processors, and the adaptive mesh refinement. So while this was always there, in Aspect 2.0, we made significant progress in some parts of these systems. So for one, we recognized that actually solving the Stokes and temperature equation can be done in very different ways. The classical scheme is to just solve the Stokes system once, then solve the temperature system, then solve the composition system, or in any other order. But if you have a nonlinear viscosity, then you might want to solve the Stokes system several times, iterate out the nonlinearity, then move on to the temperature and composition system. Or you want to iterate over all of these systems. So with Aspect 2.0, it becomes simpler to switch between these different solver schemes and also allows you to create new solver schemes that might be important for your application case. Additionally, we noticed that each of the little pieces, each of the terms in the equations are just a different module for one physical process. So with Aspect 2.0, you can easily replace some of these terms and extend, for example, the equations that you want to solve. It's still not something that can be done in the input file, but it's much simpler to do in the code right now than in previous versions. Additionally, the initial conditions and boundary conditions are often just combinations of already existing functionality. Let me explain that at an example. So this is a totally made-up model on the left-hand side. It shows the temperature field of a simple 2D box model. But oftentimes in models, you want to use a certain temperature field, like let's say an adiabatic temperature field, and then apply certain perturbations to that field, like a cold boundary layer or a certain spherical anomaly or some anomaly at the boundary conditions. All of that was provided by Aspect before, but it was provided in several different plugins. And to create your specific situation, you would have to copy some code around and create a new plugin that exactly matches the functionality that you would like to have. With the new Aspect version, you can simply, in the input file, specify several of these plugins and add them together. In this case, I just used a random background field that I read from a data file and a function plugin that describes a code region in the center that is subtracted from this other temperature. So this essentially reduces the need to change the code itself, and it allows us to remove code duplication. Additionally, we now have an option that makes it easier for users to change the input files for Aspect. So traditionally, Aspect input files are text files, like shown on this slide, where you specify different options. You can add comments to explain what you're doing at this, with this option, or what the purpose of this option is. This works very well for users who already know what options there are. But since Aspect has grown so much and we have so many options nowadays, it is hard for new users to find which options there are. All of them are listed in the manual, but now there are hundreds of these options in the manual, and it can be a tedious task to look through all of them and find the ones you are interested in. So that is why we created a little standalone additional program that can visualize these input files like in a spreadsheet view. This little program is called Aspect GUI for Graphical User Interface. It lists all of the parameters that are possible for these parameter files, including their current value and their default value. It also shows you the documentation for this parameter so that you exactly know what this parameter is doing. And you can filter default entries. So you can remove all of the entries that you actually didn't change for this particular model to focus on the ones that you are interested in. This way you can build your input file in this little program, and in the end hit the save button and you get a ready to run Aspect parameter file. And we intend to use this in particular for our tutorials, but it can also be used by any user who's just interested in having a graphical view of the available options. One final note from me before I hand over to Juliane. We are aware that backward compatibility is important. We don't intentionally break all parameter files or interfaces, and we try to keep them constant as long as possible. And we try to do that as long as possible during the development of Aspect. We intentionally decided to make some breaking changes for this version because some changes could only be made in a way that broke all parameter files. But we are aware that this is a pretty tedious task and shouldn't be repeated too often. So we will try to keep everything stable from now on again. But we also provide a way to update old parameter files and old plugins to new files by providing some scripts in the aspect/doc directory. They're called update PRM files and update source files. And by running them with an existing parameter file, they will convert the old format into the new format, and will also create a backup of the old file so that you still have the old file available. Keep in mind that since the format of these files is pretty flexible, we cannot guarantee that the script will work in any case. However, we use these scripts to update all of the parameter files that we have in our repository, and they worked for all of them. So we are pretty sure that they are good enough for nearly all cases. And with these more technical remarks, I will hand over to Juliane, who will talk about the melt solver.
It says I cannot share my screen because someone else is sharing their screen. Did you stop? Ah, yes, now it works. All right, hello everyone. I'm Juliane, and I will talk about the updates to our solver for coupled magma mantle dynamics that we did for Aspect 2.0. And so for those who are not familiar with this problem of coupled magma mantle dynamics, I will first give a short overview about the problem, and then I will go into the methods and how we improve them. So the idea behind that is that usually in Aspect we solve mantle convection equations for just one phase, for one solid mantle. And so there's the solid phase, it moves with some velocity, and there is one pressure everywhere in the domain. Now, if we want to solve coupled magma mantle dynamics, there is at least a part of the domain that is partially molten. And so in this part, there's a different phase, the melt, that also moves with a different velocity. So in this case, we have the index F for the fluid, so it's UF, and it might also have a different pressure. And so we also have to solve different equations, two-phase flow equations for the two phases. And these new equations also come with different material properties. So for melt transport, this is, for example, the permeability. So the permeability basically says how well connected are the pores of the solid rock and how easily can melt flow through. Or the compaction viscosity, which says how easy it is if like melt flows in or out of a rock for the rock to compact or dilate corresponding to that. And so these material properties like the permeability or the compaction viscosity, they are highly spatially variable, and they also depend on the solution, on the porosity itself. And so because of that, they make the problem nonlinear. So for these two-phase flow or the Mackenzie equations, if you want to know more about like how these equations are solved in other codes or to what kind of physical processes they lead, there are a number of good tutorials and introductions around that are freely available online. So you can look at some of those links if you're interested. And let's start to look at the equations that we're solving for two-phase flow. So these equations here are the normal equations in aspect that we would use for mantle convection. So there's one equation for the mass conservation of the solid, one equation for the momentum conservation of the solid, and then we also have some energy conservation equation. Now, for the coupled magma mantle dynamics, this suddenly becomes much more complex. So we now have two equations, like one for each phase for the mass conservation, also two equations for the momentum conservation, and we have to track the porosity. So the porosity tells us what is the fraction of melt at every point in time, and so we have to solve an advection equation for that too. So in the following, I will mostly concentrate on the first two equations, the first four equations, so the mechanical part of the system. So to look at that in more detail, what the first two equations say is basically just that the total mass of the solid and the fluid is conserved, and that the changes in the individual mass of the fluid and the solid are only due to reactions between the solid and the fluid. That is what this gamma, the reaction term, represents. And so that's basically just the melting and freezing reactions between the melt and the solid. For the conservation of the momentum, we have a completely new equation for the momentum of the fluid. So that's basically Darcy's law. And what it says is that the difference between the melt velocity and the solid velocity and the flux caused by that depend on the permeability of the solid rock. So how easy melt can flow through the pores, and also on the pressure gradients in the melt. And so these pressure gradients can both be caused by buoyancy forces, so because the melt has a different density than the solid, or these can be dynamic pressure gradients. And now we not only have this different melt momentum conservation equation, but also the conservation equation for the momentum of the solid has changed. So this is the part on the left. This is what we have in all mantle convection models. So basically, how does the medium correspond to shear with the shear viscosity? Now the solid can also be compacted. So basically, here, you can still hear me? Ah, okay, yeah, so somehow my microphone stopped working. Yeah, so basically the idea is that if melt flows into a part of the rock or flows out, then the rock has to correspond to that. And so there's also this compaction term in the momentum conservation of the solid here. And so these are the equations we want to solve. And so first we have to bring them into a form that makes it easy to apply the finite element method. And we did that here. So it's not important what exactly everything means in these equations. They are exactly the same equations as on this slide. We just eliminated the fluid velocity from them and introduced a different pressure, the compaction pressure, which tells us something about the pressure difference between the fluid and the solid. And so we solved these equations for this compaction pressure, for the fluid pressure, and for the solid velocity. And the way we do that is we apply the finite element method discretize it, and then we get this kind of linear system that we want to solve. And here we have the three variables we want to solve for. And basically up to here, this is how it was done in aspect 1.5. But now there's a problem with this type of formulation. And the problem is if we go to very small porosities or porosities of 0, so basically there's no melt in a part of the domain, then in this matrix, the n term, the k term, and the g term, they will all be 0. And so then if we look at what is left of the matrix, the second and the third equation are basically the same. So they are linearly dependent. And also for the two pressures, it is not clear how the pressure should be distributed between the two of them. So they are not uniquely defined. And so that means as we go to smaller and smaller porosities, we will need more and more linear solver iterations. And the system can be stabilized for 0 porosity somehow, but it will not be exactly the Stokes system for no melt present in the model. And so we sought for ways to fix that. And we had one idea that was inspired by a paper published by Todd Arbogast. And so Ryan Grove extended this work in his PhD thesis. And the idea, what we wanted to do is we replaced the compaction pressure with some variable called PC bar, so a rescaled compaction pressure. And it's defined in a way that the compaction pressure is the square root of KD, the Darcy coefficient, times this PC bar. And so the Darcy coefficient is related to the permeability, and so it scales with the porosity usually to the power of 2 or 3. And so that means for porosity going to 0, this coefficient will also go to 0. So now let's look at what that does to our linear system for 0 porosity. So in this case, we have this new linear system that has these scaling factors here. And also we multiplied the last equation by square root of KD to keep the linear system symmetric. And so now if the porosity is 0, all of these terms with square root of KD are also 0. And that means that the last equation vanishes completely. So the last equation is just 0 equals 0, and we don't have to solve it anymore. And the rest of the equations, like this term, also vanishes. And so what is left here, that's basically the Stokes system identically to what we solve if we solve a normal mantle convection model that doesn't have any melt. And so that's exactly what we want. If there's no melt in the system, we solve the mantle convection equations. And we can also constrain all of these degrees of freedom. So we don't have to solve that last equation anymore. And our solver becomes much cheaper because we don't see that increased iteration count. And to see how this constraining of the degrees of freedom looks in practice, I show an example here. So basically, if this is the porosity or melt fraction, there's some plume of rising melt. There would be a region that has a melt fraction and a region where the melt fraction is 0. And so in this region where melt is present, we would solve the two-phase flow equations. But in the region outside where there is no melt, we just solve the normal mantle convection equations. And all of the solution variables and material properties, so in this case, the compaction viscosity, they are only needed in this place where melt is present and not outside. And so to summarize this, the first step is we reformulate the equations. The second step is we constrain the degrees of freedom in such a way that we only solve the coupled system if there's really melt present. And the advantages of that are that the solver is much faster. So all of your models with melt transport should be much faster, in particular if you have a model where a large region of the domain doesn't have any melt, and there's only a small part where there's melt. And the other advantage is that we recover the Stokes system for 0 porosity. So that's the part about the linear solver. There's also a different challenge that we have for models with melt transport, and these are the reactions for melting and freezing. And so what people usually assume when they model these kind of reactions is that the melt is in thermodynamic equilibrium with the solid. And so what that means for us is that melting and freezing happen instantaneously. So they are basically infinitely fast compared to the advection of melt. But in the normal advection equation, we don't think about that problem. So the normal I've written down the advection equation, how we usually solve them in aspect down here. And so what we assume is we have a compositional field, and the change in this composition over time is related to the advection of the field and then to some reactions. And these reactions we put as a source term on the right-hand side. And what we can see here is that these source terms also depend on the solution, on the composition itself. And if you think about melting or freezing, that's certainly the case. So if we think about thermodynamic equilibrium, the equilibrium depends on the fraction of melt that is there, and it depends on the solid composition and on the melt composition. And so because these changes would basically happen instantaneously, that can lead to problems for the convergence of the nonlinear solver. And that was certainly what we saw on some of the models. And one way to fix this is to say we want to decouple these different processes. We want to decouple the advection from the reactions. And the way we implemented that in Aspect is by using an operator splitting method, where we basically say we solve those two steps differently. So we, for example, first solve the advection equation. So instead of solving this coupled equation, we first say we set the reactions to 0, solve only the advection, and this gives us an update to our compositional field. And so we use that update for the compositional field and put that into the equation for the reactions, and that then doesn't have to have any advection. So basically the reaction equations just become a system of coupled ordinary differential equations, and they are independent of each other for each point of the domain. So we just have to solve them separately in each point of the domain, which is easy to do. And so that can also be done on a different time scale than the advection. And that means it doesn't matter if these reactions are fast or if they are slow, or if it's equilibrium or disequilibrium melting, we can always solve them on the separate time scale. And that made the nonlinear solver much more robust and improved the conversions. And so these are the two main things we improved for models with melt transport. And so we also added a new cookbook to the manual that shows how these methods can be used and how they work at the example of melting in at a mid-ocean ridge. So this is the animation of that cookbook, and you can have a look at the manual to see how everything works in detail. So that was it from my side. And so I'll hand it over to Menno and the Newton solver.
Let's see. Just to find it. Let me reopen it. And there it is. Okay, I hope it's visible. What I'm going to talk about is how to solve systems of nonlinear equations in aspects, and particularly with the new Newton solver. I'm going to do this based on 3 questions. First, why is our Stokes system nonlinear? Secondly, how can we solve these nonlinear equations? And thirdly, how can you actually use it in aspects? So first of all, let's start out with the basics. Why is our Stokes system nonlinear? And as you already saw in Juliane's talk, this is our full Stokes equation.
And I'm going to look at the incompressible case for now. And the most important thing here to note is the viscosity, which is the eta term, which if it's not dependent on anything, you have a fine linear system. But if it becomes dependent on strain rate or pressure or temperature or these kinds of things, then you get all kinds of nonlinearities in there. And we know from rock experiments that actually rocks can behave very nonlinear, like this, for example, this power law rheology you see here, where the viscosity is on the y-axis and this second invariant of strain rate is on the x-axis. And you see that the material behaves quite nonlinear. So how can we actually solve these nonlinear equations? Here we have our incompressible Stokes equation, and we discretize it. We use the find unknown method, and what we get is AX is B, where A is a big matrix dependent on the solution in X. And luckily for us, this has an internal substructure with a solution vector with the velocity u and the pressure p. And we see that the upper left corner of this A block is the part which is really dependent on the solution. And what we can do, we are interested in a solution X. What we can do is rewrite the equation like you see in the lower equation over here. And from this you can you can make an equation, an iterative solution to that, which is called the Picard iteration, where you take an initial guess, x0, you solve the system, you build A, you solve the system for X, you get x1, you put that back into the as an initial guess again, and then you iterate it over that, and you can prove that under circumstances that will converge no matter what your initial guess is. But the problem with this is that once you get closer and closer to the real solution, the convergence will become slower and slower, because it's a linear convergence you get from this iteration. A different iteration which you have is called a Newton iteration. So instead of solving for a full solution, you only solve for an update of the solution. And what you have in the J is the Jacobian matrix, which I will talk about in a minute a bit more about. The delta X is the update of the solution, and on the right-hand side, you basically have the residual of the system. So for Newton iteration, we write it like this, and this also has a very similar substructure as the substructure I showed you before. Only now delta X are the updates of the velocity and the updates of the pressure. And on the upper left corner, we have a block which is very similar to the upper left block of the previous system I showed. And what's interesting about this is that the Jacobian is made up of basically the previous system, or the A matrix plus some derivative. And if you set that derivative to 0, you get a Picard iteration, but you get a defect correction Picard iteration, which is still solving for updates. And it has some advantages. But if you want to use the full Newton system, you need to use those derivatives. One problem we actually found is in the system that the system is not guaranteed to be, the Newton system is not guaranteed to be symmetric nor positive definite. And I won't go into details what it actually means and why this is important. But in short story is that it's really bad for your linear solvers. And we actually found an optimal way of dealing with this problem, to stabilize the equations, and that I will talk about a bit of how that works. But if you want to know more about it, we're currently in the process of publishing a paper about this. So to show you how this works and what you can expect from the Newton solver, I will show you two different cases. One, a test or benchmark case, and the other one is a more real-life 3D model, which we tried our Newton solver. So let's start with the benchmark, which is called, it's published by Spiegelman. The idea is that it's a two-layer brick model where you push from both sides, and the top layer is a plastic layer, and the lower layer is a linear viscous layer. And I'm going to show you convergence results for the most difficult case where the pressure is actually coupled to the viscosity, the full pressure. So this graph may look a bit complicated, but I'll walk you through it. What you see here in the upper part, or let's start with the y-axis, is the relative nonlinear residual, which goes down, and then you have on the x-axis the amount of iterations. The top part of the figure shows the results for a coarse mesh, and the lower three figures show the results for a fine mesh. The purple dotted lines and filled lines show you what the Picard method is doing, and one is the filled line is the normal Picard method, and the dotted line is the defect correction Picard method. And the colored lines show you different settings of the Newton solver. And I want to focus here mainly on the filled lines. The filled colored lines show you the unstabilized version, where you can see that it goes down really, really fast. And the dotted lines show the stabilized version. So the filled line shows the unstabilized version, the dotted lines show the stabilized version. And the take-home message from this graph is basically that the stabilized version is a bit slower in convergence than the unstabilized version, but is faster than the Picard method. And but the stabilized version doesn't crash, where you see that on the more difficult cases, the unstabilized version actually crashes, no matter how many Picard iterations in advance you do. So now let's go to the big 3D case. I will just show you this concept graph of it, where we have a subduction zone somewhere in the middle, indicated by these arrows over here. We have this upper plate is fixed, and the rest of the lithosphere is being pushed by 45 degrees over here. We have a mantle which has open boundary conditions all around, and so it's quite a big model, quite a complex model, lots of stuff going on. And I will show you a simplified convergence graph for this problem, where we have on the y-axis the nonlinear relative residual, and on the x-axis the number of iterations, and I've stopped the graph at 500 iterations. And the red line here indicates a Picard method, and the green line indicates the Newton method. And what happens here is that when you hit 10 to the minus 6, a new time step is started. So it's an evolutionary problem. And you can see that, well, the first iteration is hard, but you can see that Newton method is actually getting many more time steps done in the same amount of iterations. So that shows you that the Newton iteration actually works as expected, also on these big 3D models. So we're actually still looking at how we can optimize this Newton solver for these big 3D problems, because there are still some things to work out, but we hope to show that in the upcoming paper. So now to the question, how can you actually use it in Aspect? That's all through the input file, the PRM file, which you've seen before. And the most important thing you need to set is set nonlinear solver scheme to Newton-Stokes. I showed here the most important parameters for the Newton solver, but I won't discuss them all in the interest of time. I only will pick out a few, which are first of all these stabilization parameters. So what you saw is in the Spiegelman benchmark. You saw that the unstabilized version actually was faster in converging, but it doesn't converge. It doesn't always converge. And the stabilized version actually always converges or doesn't crash, and but can be slower. So what you can do is use the unstabilized version of the Newton solver, and when the linear solver crashes, you can set a failsafe, which is this failsafe option here, that it automatically turns on the stabilization for the rest of the time step, and it will continue. It will start again at the point it left and continue converging until the new time step, and then it will reset itself to the previous values. Another thing I want to point out here are globalization parameters. Like I said, the Newton solver is not globally convergent. It only converges when you're close to the solution. So what you see here in this problem file is that I've said that it first tries to do Picard iterations, and when I've reached a tolerance of 10 to the minus 3, I will switch on my Newton solver, or when I reach the maximum of 10 Picard iteration, I will switch on the Newton solver. The last thing I want to point out here is the line search. The idea behind the line search is that although your Newton direction you get from the Newton solve might be correct, it might go too far, and the idea behind is that you can iteratively scale your search back so up to a point that the residual is sufficiently smaller than the previous residual, and this can also help in global convergence. So to conclude, I hope I've showed you how what this Newton solver does and how it compares with what was previously in Aspect, and so that it also works for realistic test cases, realistic dynamic problems, and that we found a problem a fundamental problem with the Newton system, and we found a way to actually get it to work. So with this, I will hand over the screen to, let's see, how do I stop sharing? Yeah, I will hand over the screen to John.
Great. Thank you, Menno, Juliane, and Rene. And in a second, we'll get to the Q&A session. But for now, I just wanted to make a few quick points about Aspect. And the first of those is, so you just saw a lot of the features which have just been released in Aspect 2.0, but Aspect is constantly being developed, and right now there is a very large community working on a wide range of features. And some of those features you can expect to see over the next year or so includes we're going to significantly expand the documentation of various features, either through documentation of the source code manual or through cookbooks. Also, the addition of a geometric multi-grid preconditioner, which will help us go out to much larger scaling values, so maybe up to tens of thousands of CPUs and much better memory performance. We're working on coupling the surface processes codes, viscoelastic and viscoelastic plastic deformation, and then combine brittle deformation with two-phase flow, so thinking about brittle deformation in the presence of melt or volatile phases, and then also the adjoint method. And then if you would like to keep up to date on these changes, because they're constantly being added, you can follow the Aspect Development branch. That's at github.com/geodynamics/aspect. You can expect to see a large number of developments on this front during the Aspect Hackathon. That is when a number of us get together and sit down for around 10 days and code away. That'll be June 18th through 28th. And if you have any questions in the meantime or at any point, you can always email the Aspect mailing list at aspectdevel@geodynamics.org. And then the last point before I turn it over to a question and answer session is oftentimes there's questions about how to cite these codes, not just Aspect, but any code through CIG. And what you can do is you can go to the CIG citation attribution builder. This is at geodynamics.org/CIG/ABC. And what you can do, what I'm showing right here is I've selected the code Aspect, and then I've selected version 2.0, and then I've selected a text format. And what it does is it produces all the relevant citations for that code and that version and in this format. And then for additional citation information for Aspect, so for specific features, you can also go to aspect.geodynamics.org/cite.html. And with that, I will now open it up to questions. And thanks again to the speakers.
Hello, this is Garrett Ito.
Hi, Garrett.
Hi, this is all very exciting. Looks like you guys are tackling some really cutting edge problems and putting in some really nice functionality. This is really nice. I wanted to ask Juliane about the melting aspect. You did mention it does freezing. So lots of times, well, certainly if we want to simulate volcanic systems, the melt rises to the surface and erupts. Is there a way of simulating that process in terms of basically removing the melt from the mantle, not necessarily in building the crust, but how do you remove the melt from the mantle, or is it necessarily stuck and does it necessarily freeze to the lithosphere?
So like one problem, so what you can do is like removing the melt also in form of a reaction. So basically say, I treat that as like, so at the moment that's not implemented any material model, but should not be too difficult to say I treat it as a freezing reaction, but I just remove the mass from the system. So that would be possible. What you cannot do is taking that and adding it somewhere else. And that's the problem of the unstructured mesh that we use in Aspect. So because we have the capability to do adaptive mesh refinement, that means the mesh has to be unstructured. And you cannot just say, oh, I take out the melt here and I add it somewhere else. But so basically the options you have is just taking it out by one of these reactions. Or you can also say you have something like a disequilibrium freezing reaction, and so you just let it move until it reaches the surface. And once it reaches the surface, you can implement or like choose a boundary condition that lets the melt leave the domain. But then I guess for volcanic eruptions, the question is also at the moment, we do not have this treatment of how melt would move through the lithosphere. So that's something that John mentioned that we're working on, but at the moment, that's not in Aspect. So like basically at the moment, you can model the migration of melt through the mantle, so as long as the rheology is viscous, but we don't have hydrofractures in there.
Oh, great. Good, thanks. I did have a quick question to Menno, about the Spiegelman benchmark. So you were able to get, I didn't quite understand all three panels, but you were able to get the system to converge consistently, which was in contrast to what the Spiegelman et al. Found. Maybe Menno needs to turn on his microphone.
Yep, I'm unmuting him, or I can unmute him. Menno has to do that.
Yeah, sorry. Okay, so the problem with the Spiegelman paper is that they show a figure, or they showed results for a mesh which is refined in all kinds of areas and then unrefined in all kinds of other areas, which is very hard to reproduce for me. So what I showed in the figures, I showed you figures for very defined meshes, or very coarse meshes, and there you could see that for coarse meshes, I could get some of the cases to actually converge to very low tolerances. But when I moved to really high resolutions, about the same resolutions which they used for the finest meshes, then you could see that only for the easier cases, I could get it to converge. But for the more difficult cases, well, there was convergence, but the convergence is really, really slow. So basically, their point still holds. But we found, I think, one of the problems they had, but it doesn't solve the whole problem they tried to talk about in that paper.
Okay, great. Thanks very much.
May I ask a question? This is Alessandro Forte.
Yes, please go ahead.
First of all, thank you for an inspiring presentation. I'm really genuinely impressed. Good work to all of you. I have a question because I'm someone who generally works in 3 dimensions, in spherical geometry, rather than primarily the 2 dimensions in which I've seen many of the papers published. And one of the things that we've come across in running aspect here in our group in 3 dimensions spherical is the issue of the amplitude of the lateral rheology or 3-dimensional rheology variations that are permitted for the Stokes solver to actually converge. We've noticed very often if the variability of the rheology of the effect of viscosity becomes too large, the Stokes solver simply never converges. This might have to do with the way mesh refinement is working, possibly. Other tolerances that I'm not aware of. But have you come across this distinction between running in 2D and 3D and how that affects the convergence properties when you're specifically looking at the impact of variability in the viscosity itself?
So I could say something about it. So it's something I also saw in 2D cases. So I'm not sure if it's exactly the same thing. But what I noticed that when I used plastic rheologies, which in our cases are mesh dependent, that you get into trouble when your mesh is changing a lot in that plastic region. So what you can do to prevent that is make sure in the plastic region that you use a constant mesh size. And I think there are currently already some possibilities in aspect to do that, but there's also a branch which I can point you out, which has some code to actually do that quite neatly. Another thing, you say that what you can also do is there are some options to make sure that within one cell, you have the same viscosity, to do some averaging on that. And that also helps a lot for the Stokes solver.
Okay. Okay, yeah, these are becoming more technical issues at this point. I just wanted to confront the 2D versus 3D performance. And I think you're right. Obviously, the way the adaptive mesh refinement is actually carried out specifically is going to affect the convergence properties. And this is something we're still experimenting on, but it is frustrating, and it's led to some publications which have used Aspect basically to simply truncate the maximum variability of the viscosity so it never exceeds a certain range. And of course, that's somewhat artificial because then we're not fully experimenting with the realism of the rheology itself. We're always truncating it. And if we could eventually get around that truncation problem, that would be, of course, an enormous step.
Yeah, maybe I can add a few points here. So we experienced, I would say, similar things. In particular, that the maximum viscosity variation that you can use in a 3D model is generally somewhat smaller than in the 2D models. One of the options that really helps in this regard is what Menno mentioned last, the averaging of material properties on a cell. Yes. Is helping a lot in terms of convergence, in particular also in 3D. One more point could be that setting up the finite element mesh in a 3D spherical geometry is actually a relatively hard problem to get finite elements with uniform aspect ratios and meshes that still represent the sphere accurately. There have been some progress in DL2 and therefore also in aspect in the newer versions. So it might be worthwhile to check that again with DL2 9.0 and aspect 2.0, because the mesh should better approximate the spherical geometry. But as Menno mentioned, the option to average material properties over a cell is usually very helpful in that regard.
Okay, thank you. Thank you all. That's very helpful. Thanks.
You're welcome.
Alejandro, there was a question from Max Rudolph to you, which was asking how much variability of viscosity is included in your models, where you are finding those issues.
Well, first of all, there are issues with the radial variations of the viscosity. Sometimes we've just experimented with models where we have a one-dimensional profile, not even lateral variations. And if the gradients in the radial profile are strong, we found some difficulty in the convergence. In terms of the lateral variability, we found that beyond 3 or 4 orders of magnitude, then we found the Stokes solver was not converging. And I don't know if that fully addresses the question.
I am one there, and is this in the linear solver convergence behavior?
From memory, yes, although I'd have to go back and check the actual output. I'm not sure.
I am not sure if this is potentially one problem, but there is a parameter which is the reference viscosity. And depending on what the reference viscosity is set to, this can affect the linear solver convergence behavior quite a bit in some cases. But then again, I'm not sure if that's the issue.
Okay. Okay, thank you very much for that.
Yeah.
Okay, so there was a question from Ravi in the chat. That is, I was testing aspect and ran into some failures, sent a message to the aspect devel list, but it hasn't shown up yet. Is this normal, or do I need credentials to post to the list? As far as I know, you don't need credentials to.
I got the message, so it's.
Oh,
so,
yeah.
Like,
so I was about to say sometimes it takes a few hours. If you, for example, send for the first time, then sometimes the message need to be approved by a moderator. So it can take a few hours in the worst case, but usually the message shows up. at some point.
And also you might not get it if you were the person who sent it. So you don't see when it shows up, but we got it. And so I think the question was like, how do you know how close are your test results on your local machine to the tests that the aspect tester or like the official tester generates? And you are right, you can go into the tests directory that has the reference outputs for all of the different tests. And so if you run a test and it's failing, so if you run the test with the -v option and it's failing, it basically, like, it has a line that says check, and then it shows you the location of both of the files that are different, and you can just do a diff or like some program that compares the two files, and you see exactly what the difference between those two files is. And usually the difference should be very small, so something like 4th or 5th decimal place.
Yep, and one follow-up point on that, if you send an email and you're subscribed to Aspect Develop, as Juliana said, you may not get that email, but you can check to see if it went through at the online archives of that, and I've posted the link to that in the chat window.
Although, in general, it is useful to sign up on the mailing list to receive the answers if people just reply to the mailing list. If you're not subscribed, then you will not see what people answer to your email.
We're working on it.
I think you need to repeat the question.
Yeah, so the question was, when would the coupled brittle deformation and two-phase flow become available? And so I guess, yeah, so it depends on when we will have time to work on that. And also the other point is, like, so far there's, like, I know only of one publication that actually has included this effect, and it's very numerically difficult to get the solver to converge in all cases. So we want to make sure that we do not only implement it, but that we also test it for a number of cases. And so I guess we're talking about the next, in the best case, half a year, but probably longer. So, but we try to do that, of course, as fast as we can, because it's something that many people are interested in, but it might just take some time. Yeah, I don't know if you want to add something to that.
No.
Okay.
I guess I will add one point on that, is that a number of these features we're working on are actually in open pull requests, and so you can see how they evolve over time, and you're welcome to look at them and maybe try using them, but there are absolutely zero guarantees anything that is not merged in the code will work. But if you're interested on how we're working on the problem and the evolution of the code itself, you're welcome to check out those pull requests. But again, absolutely no guarantees anything in there is going to work properly until it's merged into the code. Are there any other questions? Okay, well, in that case, if there are no more questions, I think we will sign off. Thanks again to Rene, Juliane, and Menno for the great talks. And again, if you have any questions, feel free to email us directly or on Aspect Develop. Thanks again, everyone.